All right, so it looks like it's 10 o'clock here in Finland, and we are live on our deep dive in semantic layers. So welcome everyone. We have in total 1 hour. So first 45 minutes we will walk through the deep dive, and in the end we have some time for the questions. So let's kick things off right away, as we have quite a lot in our plates today. So first, quickly on the agenda, first a bit of an intro. What is Solita? Who are we here talking with you? Then we will walk a bit about the problem statement in this kind of semantics overall. Then there's this a bit provocative comment on why we should stop calling it the semantic layer. Then we walk through a bit about the knowledge graphs, and then how we can enhance AI with knowledge graph to a graph rack, and then we have some closing remarks, and finally some time for the Q&A. But yeah, let's start with the intros. So first, what is Solita? So we are an organization with over 2,000 people operating in nine countries, mainly Nordics and Central Europe. We are a consultation company doing a lot of different areas, basically covering business, technologies, people aspects. So we have design, strategy, data, AI, cloud, connectivity, software development. So quite comprehensive understanding in this area. And then who are we talking here today? My name is Juha-Pekka Joutsenlahti. I'm a data advisor at Solita, been here in about 7 years, been doing various things around data catalogs, information architecture, semantics, and areas related to those. And then together with me here we have a Per.
Yes, hey, my name is Per Olqvist. I'm head of enterprise design here in Sweden for Solita. And I have a long background within enterprise architecture and also information architecture, especially conceptual information modeling. So I guess we'll take it away, Juha-Pekka.
Yes, sure. And to begin with, here's a bit of a disclaimer. So when we are talking about these data and information management related topics, there is not a kind of single absolute truth, but this is more like collection of our premises, experiences, what we have seen and learned in our journeys. So yeah, there might be various different viewpoints, and this is kind of one of the stories. But yeah, if we start from this kind of first point, so nowadays when we are thinking about the AI, it's not the computational power which is the kind of biggest obstacle for us today, but it's capturing the meaning of things. And that's pretty much what is our focus and theme for today's deep dive. And then when thinking about the semantics and why do they matter, so here's an example of some quite traditional questions that might be asked from the business in conversations or built in the or answered by the BI reports. And all of these questions, they can hide a lot of semantics behind them. There's a lot of kind of ambiguity hidden, and typically we tend to resolve them without even thinking it really through. So for example, when we are talking or asking, is this order completed? What do we actually mean by completed? Is it when the order has been shipped or delivered, invoiced, or paid? So what is kind of actually completed order in our kind of domain? Or second example, how many customers do we have? Are we talking about the active customers, our all-time customers, only the legal entities, or all the accounts we have in our CRM system, for example? So there's a lot of these little devilish details that often cause a lot of headache for us. And there's basically similar examples for each of these. So there's a lot of these kind of nuances that we need to somehow resolve and identify, and that's pretty much the semantics we are talking about today, and kind of diving deeper into. But first, if we have a look, a bit of a recap on this kind of evolution of semantics, especially in this kind of data and information area. So it started pretty much on the 1970s. So basically, it was this entity relationship modeling article by Peter Chen, which is probably many academics, at least, who have been writing anything in this area are very familiar with this one. Then on the 80s came the first early ontologies. Of course, kind of the ontological study as such is more of a kind of philosophical thing, and it goes way back to this kind of ancient Greek, where the philosophers were thinking about these topics. But this is where it basically came into this information and data world. Then on the 90s, the first semantic layers for business intelligence came into the picture. 2000 was where the semantic web linked data emerged. Then 2010s, it's where this kind of topic of knowledge graphs came into the picture. I think it was 2012 when Google announced their knowledge graph, for example. And these are, as said, not the years or the timelines where these were invented, but more of a kind of timeline that when did these things became kind of popular in organizations. Then a couple of years ago, we started to talk a lot about this AI-driven context. So the Gen AI LLMs came into the picture, and we soon identified about this AI hallucination and how the AI is really kind of needing this contextual understanding. Last year, it was a lot about this context graphs, which is then thought to be the next evolution of knowledge graphs. And that's pretty much where we are at the moment. And then what does the future will bring us? We do not really know, but one guess is that we might be approaching within a few years time frame into this kind of so-called semantic fidelity systems, meaning that we are able to build systems that are actually able to preserve the meaning across the whole kind of lifeline of the data, from the kind of creation through transformations all the way to this kind of end user and the applications. But yeah, we shall see where this takes us. And then to better understand semantics, there is also one slide about this kind of understanding the nature of data. So when we are talking about data and what data is, it is essentially a digital replica of some real world event or actor. and that's very important to understand also in the context of semantics. So whether we have orders, payments, contracts, some approvals, or even some IoT sensor readings, they are all somehow connected into some real world event. And when we start thinking this data as a digital reflection of a real world, we will acknowledge that the value of the data is actually that how well and how accurately it can capture that real world event. And that's basically semantics. But next, Per will tell you a bit about this problem field.
Yes, and I would like to take us back in time to reflect on two evolutions or trends here. And the first one is from the developer perspective and talking about higher abstraction. Back in the days, some of us started our careers writing low-level machine code. We were managing memory pointers and stack operations and even simulating Turing machines. Then, with each generation of new programming languages, we abstracted away from the technical details and the hardware. We stopped worrying about memory allocation and focused instead on business logic, user experience, and outcomes. And today, with AI and so-called vibe coding, we're taking another leap. We describe what we want in natural language, in plain English, and then let AI write the actual code. This is, of course, powerful. Instead of having to learn a formal programming language with strict syntax, we simply use our own language. But this also introduces a critical new challenge that no previous abstraction has faced. That is the fact that human language is fundamentally ambiguous. Another trend here or evolution from the user perspective is that we have lower detail control today. From the beginning, we used manual tools like pen and calculators to run business transactions, and we were in total control of every step. Then we introduced IT applications where we still control steps by clicking, entering, and submitting transactions. And then we more and more began to automate sub-processes and triggering workflows. However, some steps were monitored and manually approved. And now today with agentic AI, we're doing something fundamentally different. We're deploying teams of autonomous agents to solve problems. And they may take a path we didn't predict. They, quote, reason, unquote. They collaborate, they make decisions, and based on their interpretation of our, again, natural language instructions. And nowadays we specify the goal, success criteria, and hopefully the constraints, and let AI take control of the tool selection, the approach, and so on. So in summary, we have gone from controlling both development and usage of tools to letting the LLMs and AI interpret our intentions. We have gone from controlling the how to expressing the what. And to understand what we mean has always been a challenge, but now misunderstanding can be more critical than ever before. And misunderstanding can be easier than you think. Whenever you are exposed to a foreign language that you do not know, you know that you don't understand. So the risk is quite low because you would ask help for translation. In some cases, not even your mother tongue can help you when some subject matter expert talks about detailed topics that you are not familiar with. It can sometimes even feel like a foreign language. The risk is still manageable because you would probably ask questions to understand what is said. But the real danger is not when it's obvious that you don't understand the meaning. The real problem starts without you even knowing about it. When you believe that you understand, but in fact have a quite different understanding than was the intention. We have went from unrecognizable language, terms, and then the hidden ambiguity. This can be illustrated by the classical debate of what customer really means. In the same company, it typically means slightly different things. We see a semantic drift in action. Same word, completely different meanings. And this is what linguists call homonyms. And it's everywhere in our business language. In our organizations, we have over time built in this kind of hidden ambiguity in different departments and domain. And the semantic drift is a fact. But the difference today is the scale and speed. Since we're now facing the same risk, deploying specialized agents that are trained on our own domain languages. One agent, one mistake, manageable. But agents operate at machine scale, so it easily becomes millions of wrong actions. And we usually don't discover the mistakes until it's too late and the damage is already done. So both humans and machines need some sort of semantic backbone of shared meaning. Maybe you remember the Greek myth about King Midas that wished for that everything he touched would turn into gold. Well, his wish was granted. He got exactly what he asked for, but not what he meant. When he touched his daughter, she became a golden statue. And when he tried to eat, his food turned into gold. And this is precisely the risk we face today. AI execute our instructions, but they interpret our words, not necessarily understanding our intentions. And this amplifies the King Midas problem exponentially. What seems obvious to us is not obvious to machine. Now, if we try to summarize these challenges we are facing, we could say that first, we face more abstraction. We communicate in ambiguous natural language. We went from formal code to plain English. Secondly, we have now less control. We've handed over execution to autonomous agents, even more critical to express intentions with clarity. And AI scales. It scales ambiguity at machine speed, and one misunderstanding becomes easily millions of wrong decisions. And the semantic depth, decades of implicit fragmented meaning. AI has nothing stable to ground itself on. And the answer should be something like machine-readable semantics, formal definitions, explicit rules, and clear boundaries, context that both we and AI can actually understand. So back to you, Juha-Pekka, to take on.
Yes, thank you. So yeah, next is this area on why or what is the problem with this semantic layer. And even if this statement might be a bit provocative, it's still kind of, well, you will soon see. But I think that kind of the main problem with the semantic layer is that as a concept, it's very vague and even loaded concept. So when someone asks to build a semantic layer or fix the broken one, the question is often, what are we exactly going to do? And I think it's quite ironic that the kind of the problem with the semantic layer concept is the ambiguity behind it. But maybe, and this is now the statement. So what if the semantic layer is not a single layer at all, but more of this kind of a meta model consisting multiple dimension, and each of them have a separate semantic responsibilities with some guarantees on certain aspects of the semantics. Yeah, just a thought and food for thought on this. And I will walk through that what would those dimensions then be. So of course, the first one is the data. It's a kind of a record of reality, and it does not really interpret it. So it only explains what happened. It captures some real world event, in this case, an order in a digital format. So quite obvious one. But then after that, we will go kind of into the more deep semantics areas. And the second layer, I would call it the semantic grounding layer. And this is what I would believe most people nowadays call as a semantic layer. And the purpose of this is to stabilize the way we are reading and understanding the data. So having kind of or ensuring that we are talking about the same things. Well, this is mainly kind of master data and harmonizing that the same customer ID means the same customer across the platforms. Also organizing and structuring data, so aligning and ensuring that our data structure aligns across these different platforms. And also how we are interpreting and understanding data. So standardizing how we, well, as said, understand the data. So how do we define, for example, BI metrics and dimensions? And all this is very important and actually path to kind of start building this business understanding on top of the data. And quite many of the tech vendors are currently doing this, and this is kind of evolving in a quite rapid speed, but this itself is not enough to fully cover the semantics. So the next layer is this kind of the ontological dimension, and the idea of this dimension is to define the business meaning of things and their relationships. So what is this completed order in reality? What relationships are defining the domain we are operating in? What are the boundaries? What must be true? What cannot be true? And so on. So it basically defines that what this concept mean for the business in a business language. And this is something that is currently emerging topic and something we are also now focusing in this presentation, that how to build this kind of ontological understanding. But then there is also the fourth dimension, which is this spatial and temporal one. And this is a bit tricky one, because this is something that we are seeing that is, well, in early stages of its maturity. It's kind of still mainly academic. There is some kind of practical examples. We are seeing some early signals of this, and this is something, for example, where these context graphs are operating in and why they were so hyped last year. So this spatial and temporal semantics, it tells you when something is true, how it evolves over time, what were the conditions, what was the kind of context in the kind of time of the event. So yeah, it's kind of the time dimension we also need to understand. So what were, for example, the original terms at the time when the order was placed? How is it changed over time? If there was some change in the delivery, for example, the delivery dates, why did that occur? Who authorized those changes? And over what was the business context at that moment? And then the big question might be that why does this kind of distinction matter? Well, here is some of the reasons for it. And I think the first reason is that it prevents this so-called semantic compression. So when we are mixing together the data definitions, business rules, and if we are bundling them up in a single layer, we will often end up in a quite messy situation. And also, it kind of clarifies the ownership and supports the governance when we make the distinction that who owns the data itself, who owns the data dictionary, who owns the kind of business logic behind it. And it also helps us to understand these data quality problems, because we can point out whether it's the kind of data pipeline that is broken, whether it's some aggregation logic behind it, or whether it's just the wrong interpretation we had over things. It anchors the this truth anchor, so it kind of connects that what actually happened in the real world to what the system actually thinks that happened. The fifth point, it's of course the guardrails for the AI. So as discussed, we need some way to provide this contextual understanding for the AI for it to stop hallucinating, and also it allows us to change and evolve things without this semantic drift. So when we have these clear semantic responsibilities, the changes occurring, it does not as easily break things up. So that's the reasoning for kind of making a clear meta model and distinction between these different kind of semantics aspects that we need to consider in building this kind of context layer within an organization. But then, Per, please take it away.
Yes, let's talk a little bit more about a knowledge graph. And I think we could start with a quote from Mike Dillinger, who quoted quite nicely, I think. He says that it's a cognitive map for machines. Personally, I would add it's also for us humans. You could say that it's a structured representation of knowledge that uses a graph-based data model to capture entities and their relationships. But what does that look like? Let's first have a simplified look at the evolution of data management over the years. First, we have the classical relational tables. This is where most of us started. Rows, columns, foreign keys, everything flattened into tables of entities. It's structured, but quite rigid. Then we have added a growing volume of semi and unstructured data in documents. We added flexibility and a lot of file formats, but it's usually siloed. It's often hard to find connections between the documents. It's flexible, but also in a way isolated. Recently, we moved into vectors and vector search, and with AI, we can now find similarities. Show me things like this: math-based proximity, but it lacks explicit logical rules. It's all about probability and approximations. So now is the time to rediscover graphs. This is where relationships becomes the first-class citizens and in focus. We don't just store data entities, we also capture how things actually relate to each other. So what does a graph look like? Let's have a quick look on a simple set of data. On the left-hand side here, we see the traditional relational tables, optimized to store entities. One table for each type of entity. And the relationships here are, in a way, implicit and by foreign keys. Now, the exact same data, but in a completely different structure on the right-hand side. Every relationship is now explicit, it's visible. The data tells you how things connect, and you don't have to infer it from foreign keys or construct it with joins. Notice the difference. In the tables, relationships are implicit, hidden in the keys, and discovered through joins. In graphs, relationships are explicit. They're actual data with meaning attached. And if we have a closer look, we could have an example of a real-world question within medicine. If we want to find drugs that target proteins involved in Alzheimer's. So on the first screen here, we see the traditional approach. You have the three tables of drugs, proteins, and diseases, each with their own columns and primary and foreign keys. To answer the question, you have to find out the relationships and join the drugs to proteins and proteins to diseases. And then you filter on the disease name. This finds the facts, and you get the listing matching records. But with more tables and joins, it gets complex really fast, and performance issues are growing exponentially. The similar on the right-hand side, but now in graph, completely different approach. You don't join the tables, you traverse the relationships in the graph. You follow it. Drug targets protein, protein involved in Alzheimer's. And you actually see the pathway visually. Drug X targets protein Y, which is involved in Alzheimer's. But in the total graph, this protein also interacts with other proteins, which are affected by other drugs, which have side effects. And this is a very clear example in the health industry. The query here is far more simple and effective, and also readable to humans. So how are these graphs now constructed and built? At its core, it's very simple. It's only two basic building blocks. The first one here are nodes. These are the entities, the nouns of our data world. People, places, concepts, like companies. And here is the example of Alice and Google. The next are edges, relationships, the verbs that define how nodes connect. In this case, works at. And together, they form a triple: subject, predicate, and object. Alice works at Google. And this is the atomic building block of a knowledge graph. And you can chain these together, of course, that Alice works at Google, Google is located in California, etc., etc. Building a web of knowledge from simple triples. So let's take a look at another example of real data. This is a classic, books and authors. And you see what we have captured here, not just the facts, but in a way, meaning. We know followed by is a temporal relationship, sequels. We know has author is a creative relationship. We know located in is geographical. And when we and AI traverses this graph, it doesn't just see data points. It understands the type of connection between them, the type of semantic understanding. But how do we ensure that these relationships are used correctly? Can anything be connected to just anything? That's where the ontology comes in. You could see the ontology as the rule book for your knowledge graph. You see here that the instances, the real entities, are not present. These are the concepts and how they relate. Think of it like grammar for knowledge. It defines valid relationships. Books have authors. Authors are located in places, and books can follow other books. Without this, knowledge graphs are just connections. But with this, they structured meaning that AI can rely on. And this is the kind of semantic backbone that support both humans and machines to not understand our natural language. Now, in some more regulated and mature industries like finance, medicine, healthcare, etc., ontologies have already been used in practice for years. For example, FIBO and SNOMED. Then others are emerging in specific industries like product supply chain, food, and e-commerce, and more. But I would say that in addition to these existing standards, you probably have your own semantics in your organization, which reflects your specific knowledge, what makes you unique on the market. And please remember that the more AI can understand your specific context, rather than what can be found in general on the net, the better it can support you. To summarize, I think McKinsey caught it quite good in their recent report this year, that semantic layer turns data into knowledge and is most often implemented through ontologies and knowledge graphs. Now, maybe you say, show me the evidence, what can it look like in practice and what value can be measured? So, thanks for asking. Let's have a look. Here we have two of the very first published research papers that actually benchmarked LLM models' accuracy on enterprise SQL databases with and without ontology-based knowledge graphs. And the results were quite clear. Semantics makes a difference. So how was this actually tested? First of all, they had a baseline, direct text to SQL. And here they used GPT-4 to create queries on a database. Secondly, they have an alternative approach where they introduced a layer of knowledge graph based on an ontology. And the third approach, then they added also what they called ontology-driven check. So it, in practice, evaluated the query against ontology rules and repaired them when possible. And it's worth noting that when it was not possible to repair, it actually reports unknown answer, as an opposite from most hallucinations we see in the LLM world. So now these three approaches were then tested against 4 different set of scenarios, where complexity comes from 2 sources: the question itself and the schema complexity. You see it on the X and Y axis here. And that gives 4 scenarios over low and high complexity. Let's have a look at what could be examples of those questions. In the first one, the low schema complexity and the low question complexity, it's about basic reporting. It's a projection over 3 columns and 1 table. The example here is return all claims we have by claim number, open date and close date. Pretty straightforward. The other one coming next is a little bit more complexity about the question. It's including mathematical functions and aggregations and comes over 4 tables. And the third one with a more high schema complexity, but still low question complexity, is about 6 tables. And the last and fourth, which is called high complexity here, is then adding some mathematical functions, aggregations, and crosses 9 tables. And just bear in mind that 9 tables in the production environment is quite limited. So probably you will have systems with a lot more tables and even more complex calculations here. But nevertheless, so here on the left-hand side, we first see the results on the low schema complexity. And on the left-hand side bars, you see the results from the straight baseline text to SQL. And it gives some results, but in comparison to the other bars in the middle and on the right-hand side, the difference is clear. So somewhere between 25 and 40% you could have with the text to SQL, but it almost double or a little bit more with the semantic support. Then what happens when we add the schema complexity? Then the text to SQL collapses into 0% accuracy. A suggested explanation here is that without the semantic backbone, the LLM is forced to guess on the implicit business logic and struggles with complex many-to-many relationships and multiple joins. With these results, you might be thinking, okay, I see a point here that ontology and knowledge graph indeed can help, but the results are still far from perfect. What if full accuracy is required? Furthermore, you could argue that these research results were from 23 and 24, a couple of years ago. So what about now? Haven't the models gotten better? And again, happy that you asked, great questions, and yes, they have improved. As a matter of fact, just recently, there was an update of this benchmark made by Jason and his colleagues here. And it's all open source and available at DBT Labs homepage. It's also worth mentioning that they had a little bit more modern technical framework. So that's why the GPT-4 comparison here is not 0%. And you see still text to SQL struggles in the GPT-4 models. And the semantic backbone is giving us better results. And the key findings here is that even state-of-the-art models struggle without the semantic context. And the colored sections on top of here is the result when they added some more tables and more modeling. It's a matter of denormalization and additional semantics. And in those cases, you were actually getting 100% accuracy. So the best effect is obviously when you combine the results from the data modeling low level bottom up and the one that semantics and ontologies gives you from the top down. So I hope this gave you some insights on how ontologies and knowledge graphs can add value in this context. So over to you, Pekka.
Yes, so let's go through a kind of this case example with how to enhance this AI with the graph rag. So this is quite a simplified illustration of a quite traditional setup. So someone asked AI a question, then there's an AI agent, some AI orchestration maybe, who start to work to find the answer. And it needs to find both the actual data, but also the context around it. And here, as a quick reference, this is just an illustration from Neo4j's announcement from a couple of weeks ago, where they announced a partnership with Databricks. And this is an example of a setup where they are building these graph capabilities on top of the data platform to enable AI to execute some more advanced reasoning through the graph. But this is still kind of very much data oriented. So the question is that how can we capture the business meaning around it? And this is kind of a quite traditional setup most of the organizations currently have. So we have the data platform setup on top of which we have built this BI chatbot doing some text to SQL. But what is currently missing here? Well, first of all, we have a lot of this unstructured data we need access to. And this is where this kind of the traditional RAGs, the vector database, coming to the picture. So we can bring in these unstructured documents into the scope for the AI. But this alone is still not enough. But what we also need is this graph rag capability, which can bring together all the structured data, unstructured data, but also other knowledge sources that exists into the organization to build a more comprehensive understanding. And how to get started? So here's an example. So first we need to have some kind of an ontology or meta model. So we need to understand that what type of things we have and how are they connect to each other. And after that, we also need to make some architectural design to understand what kind of data sources are we going to bring in here. What should the solution look like on a high level? And after we have these sorted out, we have a blueprint and we can start building some graph rag capabilities. And I would say that we have three different options to start building it. And this is kind of the first one is, of course, something that is already established in many organizations. So we have a data catalog where we are already connecting this technical metadata with the business metadata. We can have the business glossary, we can have some other business rules defined, we can have even some processes included into the catalog. So that's the first path to take. The second option would be to take some standalone graph database. It seems that there's more and more coming with a quite rapid speed. So of course, Neo4j, Janus Graph, AlgoDB, GraphLDB, these are a few examples of different technologies, and there is some differences. Some is better for this kind of RDF world, some are better for this labeled property graph. So yeah. And then the third option is to take some existing graph rag. For example, the Microsoft graph rag is quite easy to set up and start to use. And then after we have this graph created, what we should do is to connect that knowledge graph into our agentic development to demonstrate and try out the value. Is this something that is providing value for our AI use cases or not? And does it improve the AI accuracy? And here's some of the learnings we have gathered so far. So first of all, the foundation is very, very important. So we need to understand the structure, what we are having, also the relationship and kind of the direction of relationships. It's just as important as the kind of objects themselves. We need to also be kind of cost sensitive. So using LLM for populating the graph might not be the smartest way, because that is a task that can be done with some NLP solution, so natural language processing or some small language models. And also, if we have kind of these duplicates or other problems with the graph, it does not really serve the purpose. Also, there is different retrieval strategies. So there's this basic one, which is basically RAG without the graph. There's the local one, so finding some node and its immediate relationships. We have the global one, which uses these pre-computed reports and summarizes more for this thematic analysis. We have a drift, which is then navigating the graph along the paths. This is something popular, for example, in the anti-money laundering cases. And then we have the hybrid, which is basically this combination of vector search and graph. So it's the graph RAG system. And then for the best practices, so learned so far. So the schema is something that is kind of a living organism. So we need to have schema to bring in some structure, but we also need to be agile enough to adjust the schema as we have new data. Then there is a lot of this overhead in with the LLMs, and especially with the graph RAG. So we also need to consider the performance. So maybe we cache some parts of the graphs that we know that are more static than maybe some other. So that's how we do not always need to rebuild this reasoning chains for every query. And also this re-ranking. So just if the graph finds something kind of close by it doesn't mean that it's necessarily relevant. So we need to add some kind of re-ranking mechanism to kind of read the query and also kind of consider it with the content retrieved together before we kind of getting it back to the LLM. But yeah, those were the learnings so far, and then some closing remarks. So Per, hopefully you
can hear me better.
Yes, now it sounds better.
Thanks. I'm so sorry for the technical hiccup here, but the closing remarks, just a couple of gentle reminders here that two things that I think we are worth reflecting on. First of all, please acknowledge the fact that we all can have different perspectives on the same topic. This does not necessarily mean that one of us is right and the other one is wrong. It can be simply the case of different point of views. And the second thing is, let's remember that even if we can strive towards theoretical perfection, it's not always worth the last effort. Try to find what's pragmatic and works good enough for your situation. So those were the two reflections that we would like to share.
Yeah.
And then the summary in total.
Yeah. So here's some kind of final verdict. So first of all, we are not sure what the future will hold, as this is kind of constantly evolving and quite early phases on the evolution of this topic. But we have seen some early signals on this. So as said, the data catalogs, there is kind of many vendors who are now rebranding the traditional catalog in something AI kind of context management system or similar. So there is a more and more need to connect this technical and business metadata capabilities. These knowledge graph and ontologies, they are not anymore only kind of this academic thing, but more and more organizations are starting to discuss this topic and have acknowledged that something like this is needed to build this semantic foundation. And of course, this kind of technical capabilities like these graph racks, context graphs are emerging topic. And also we are navigating a very unknown territory. So it requires also a lot of agility, a lot of this kind of experimental mindset, learning by doing attitude from the organizations, kind of going to this direction. And it also needs to be a strategic direction, because building this kind of contextual understanding, this kind of, in a way, brains of an organization, it needs to be a strategic commitment. That's maybe the final verdict of this. But yeah, then it's time for some questions. So I see there is some questions. Assuming an organization has no existing ontology and wants to improve an existing AI tool, what's the general timeline to do so? Asking for a friend. Yes, so I think kind of, well, there is the industry specific ontologies available, but typically kind of building on more modeling this organization, of course, comprehensively doing that, it's kind of not a small task to do. So we have those kind of conceptual modeling exercises where we are modeling the organizations, which are in large organizations can take multiple years to kind of gather that level of understanding. But as said, getting started with this is to have kind of few core pieces in place. And I would say that starting with some kind of first draft, or even use LLM to assist you to create some kind of a draft of an ontology, and then validating it and walking it through, that might be easier to get started with. Per, do you have some comment on
that? I saw another question about graphs and vectors, and I think the one that put the question on the table is quite right, that they do complement each other, and they have, it's not a successor, so to speak. So I see it as you use them together. So both the vector search and the ontologies and graph databases.
Yeah, I do agree that they are complementary, and both will have use cases that they are good at. And yeah, I think kind of neither of them will go away, but rather they will work in collaboration in different tasks for the AI. What else? Yeah, then there is a question that how do we ensure that these levels are recognized and category errors in this space are called out? Yeah, I think we are now achieving into the phase where more and more organizations are becoming to a realization that kind of the semantic layer, or what we had as a semantic grounding dimension, it's not enough alone, but also we also mean the business semantics. So I think it's kind of something that is also very much related to this kind of enterprise architecture work, and acknowledging that the data is kind of one aspect of semantics, but we also have a lot of business semantics that we need to bring into the picture. So yeah, I think it's a lot to do with the kind of communication and bringing in the message that the kind of a true understanding lies into the head of the business people and not necessarily the data platform people. Then there was a question, how would you advise organizations to utilize existing conceptual models for building up the necessary context for agentic AI layer? I think that's a good question, and I think kind of those conceptual models itself, it's already a very good starting point, and kind of what I would do probably is to consider that, okay, could we put this kind of the conceptual models? Of course, first we need to identify that, are we talking about this kind of business terms as a concept, or is it more like this vocabulary of terms and how those concepts connect, or is it kind of actual the conceptual model that how does the business operate conceptually? But yeah, yet again, identifying that which type of elements we have in our conceptual models, and then drafting some kind of a blueprint, and then starting to work to put those in some kind of graph. There is some data catalogs that support that. There is this EA process management tools that have some capabilities. So either we can connect those tools directly into some agentic flow, or we can kind of bring them together in a knowledge graph and build the foundation that way.
I saw a question also about if it makes sense to start off with the lower levels here on the data layer, that ontologies felt far-fetched, and I think you should actually do it both ways. And nowadays you also have quite good AI support to help you building the ontologies and knowledge graphs. So I mean, traditionally we have had a lot of cumbersome work manually to create this conceptual information models, but nowadays we can have the heavy lifting done by AI, and then have, of course, the human experts in the loop. But I think you need both perspectives here.
Yeah, definitely. And I think kind of it's, as said, it's easier to start to define the meaning of data. And that's probably why organizations are going that path, because it's easier to associate the meaning over the data we already have rather than starting to collect the business understanding. And that's the exact reason why it's so rare to have the business architecture properly done in organizations, because that's typically the hardest part. But then kind of as a segue from that, I like that there was mention on this CPOC modeling method. So I think that's a very useful tool to kind of start building this context graph. So what CPOC stands for, that we have the supplier, we have some input, we have a process, we have output, and we have consumer. So it kind of describes the information flow in the context of a process. So what information goes into the process, then process does some sequence of tasks, and then it outputs some information for some other process to consume. So I think that's a very effective way of modeling that kind of business understanding and building the bridge between this kind of processes and data. Yeah, I see we are running out of time here. There is still some questions that we did not have time to cover, but I think we can maybe get back to those later on. Yeah, not sure if Nina, you have something kind of that, is there a way for us to get back to those questions we did not have time to answer, but I think we can find one way or another to get back on these topics. But yeah, it's 11 o'clock here in Finland. Thank you for this. I think it was hopefully worth of your 1 hour. A lot of things, a lot of topics to cover. This is not an easy topic, and as said, a lot of different interpretation in this area early in the evolution. So it might look a lot different in 6 months. But yeah, thank you from my behalf.
Thank you so much.
Yes. Okay. Cheers. Take care. Bye.